by Masha Naslidnyk from University College London.
Thank you. So apologies if any of you saw the previous title of the talk. I was going to talk about something else, but I think for this crowd, the Bayesian quadrature work would be more interesting. So I'm a finishing PhD student at UCL, and I've done a bunch of work on kernel method Gaussian process theory, and in particular, both on Bayesian quadrature and using Bayesian quadrature for some downstream problems, and I want to talk to you about, that's what I want to talk to you about today, about two projects in that sphere. Okay, so as we've heard over and over in this workshop, integration is a common problem in both statistical computation and in general in scientific discovery and engineering applications. In statistical problems, we need to integrate to model evidence, to do model selection, or in frequentist stats to marginalize over nuisance parameters. And in science and engineering, for instance, an expectation might appear if we're interested in an expected outcome of an experiment or a simulation. And said experiment or simulation might be expensive to conduct, either in terms of time, or in terms of money, or in terms of purely feasibility and availability of data. And this is the primary area of interest for the purpose of this talk. We'll consider functions that are expensive to evaluate. So when needing to integrate them, we want our integration method to use as few samples as possible. A general framework for numerical integration, a quadrature rule, is a general framework for numerical integration where I'm approximating an integral over f with respect to some measure p as a weighted sum over evaluations of f over these xi's that I'm going to call design points with some weights wi. A standard kind of approach to this is a vanilla Monte Carlo method where I take the weights to be 1 over n, so I'm weighting all points equally, and the design points are just coming sampled from the distribution p. And Monte Carlo error is bounded as 1 over square root of n. And this typically requires a lot of samples and comes with some drawbacks, like we're not using the information about where xi's are located exactly. Like after this sampling happened, I know exactly where they are in space, so I should be able to use this information to obtain a better estimate. And also sampling from P can sometimes be challenging, so we're good to have a method that doesn't require this. And the message in Bayesian quadrature is that reweighting the design points, xi, can dramatically speed up convergence, and we'll be, and we'll be able to drop the assumption that xi come from P as well. Okay, so Bayesian quadrature is a probabilistic integration method that was introduced a while ago. Here are some seminal papers on it. It has been quiet on it for a few decades, and there's been more and more work popping up recently as the improved compute let us tackle more challenging problems, and as there's now more and more interest in the more challenging problems in general. And the and the high level thing that I guess I want to relay with this talk is that Bayesian quadrature works well when the number of samples is fairly small, which happens when the integrand is expensive to evaluate, or we have prior information about the integrand that we want to encode in our quadrature rule. Right, so a little quick summary about how Bayesian quadrature works. In Bayesian quadrature, we place a Gaussian process prior here. Well, no, the red line is already a posterior Okay, we place a Gaussian process prior with mean zero. Mean zero for the purpose of this talk, it's fairly without loss of generality, and kernel K on F, and condition this Gaussian process on the available evaluations to get the posterior GP. So here, this is a posterior GP, the red thick line, and this sausage here is plus minus 2 variance provided by the GP. Since an integral of a Gaussian process is normally distributed, this immediately gives a posterior on the integral that is normally distributed with mean, which is the BQ estimate of the integral, and some variance. This is a visualization of what that might look like. If I is the true value of the integral, then this might be the integral over this red line, and with the variance, that is the integral of this sausage in here. There are natural kind of sequential methods that can be used on top of this. If we have the ability to collect more points, we can use this setup to inform where the region of most interest is. For instance, we can just do this by maximizing the variance and saying, oh, the variance is greatest in here. Let's collect the n plus first point around here, and we'll get an even more confident, well, this is not particularly confident, we'll get a more confident estimator of the integral. I will not be talking about these active learning schemes here, so I'm just saying this verbally. Right, here is what the mean and the variance of this posterior belief about the value of the integral looks like. This mean, the BQ estimate, can be seen as the aforementioned quadrature rules, where the weights here will refer to as BQ weights from now on. And for people familiar with kernels and Gaussian processes, this is a familiar expression. If you're not super familiar with it, it will not come back. That's not super important. What I wanted to say about this is that the appearance of the kernel in the quadrature weights allows us to encode prior information about the integrand. Say if I know something about its smoothness or periodicity or non-negativity, there's all work out there on doing Bayesian quadrature with kernels that encode that information. The method comes with built-in uncertainty quantification. The variance here can be used to express how sure we are about the value, about this estimator of the integrand. Now, to the negatives, I kind of reduced the problem to another integral. And if this isn't available in closed form, then I haven't really done anything, because I still need to compute integrals. So I need to be able to evaluate the integral of the kernel against my measure of interest in closed form, which can be restrictive, but this is known for a bunch of classes of kernels, the Marchurns, the RBF, the commonly used ones, and for like uniform Gaussian mixture of Gaussians type distributions. And if this is not known, we can do a reparameterization trick where we pretend that the measure is Gaussian or something well behaved and just throw the rest under the integral, or use something called the Stein kernel, for which this thing can be assumed to be a constant. Another negative of the method is the cubic cost of the inversion here. The argument here is that this cubic cost is worth it if the benefit that I'm getting from using Bayesian quadrature, it outweighs it, and that happens when the number of evaluations is fairly low and the cost of getting an evaluation kind of drowns this cubic cost in here. And I'll give some examples of when that happens. Yes, and the main perk of the method is its improved accuracy in comparison to Monte Carlo methods. So there are many convergence results out there. For example, if I know that the function being integrated is of Sobolev smoothness S, if you're not familiar, you can think of it as it has S derivatives, weak derivatives, but yeah. And if I choose an appropriate kernel, appropriate means it's of smoothness S or higher, then the worst case error of the integration is bounded as such, where S is the smoothness of the function and D is the dimensionality of the problem. And this, of course, is an improvement over the Monte Carlo error that I mentioned earlier of 1 over square root of n. So hopefully this is motivating information that if I'm integrating, for example, if I'm integrating something sufficiently smooth, did I put this in? Great. If I'm integrating something sufficiently smooth and sufficiently low to mid-dimensional, then I'm getting convergence rates that are a lot better than Monte Carlo. Or in other words, this is making better use of the available n samples than Monte Carlo does. Okay, are there any questions at this point? Yes. One slide back?
Yeah.
This?
The D is the distribution.
The D is the dimensionality of the input space. Right, so the first project that I wanted to talk to you about is using Bayesian quadrature to estimate MMD better in scenarios where the measure that in a scenario where one of the measures under the MD is the output of a simulator. And yeah, this is the paper. Something is happening here. Right, as I'm sure you've heard introductions to maximum mean discrepancy multiple times now, so I'll just go over this fairly quickly. Maximum mean discrepancy is a distance measure on probability distributions that measures the difference between probability distributions by the distance between their kernel mean embeddings. And the kernel mean embeddings lie in the reproducing kernel Hilbert space of some kernel of choice, and they're defined as the integral of the kernel with respect to the measure. Now, of course, in a practical scenario, I will likely not have access to the exact distributions. Instead, I might only have, let's say, m samples from the distribution p theta and n samples from q. So I'm going to need to estimate this kernel mean embedding, which is an integral. A default in some sense way could be to compute a Monte Carlo estimate, which is just an equally weighted sum of the kernel evaluations, where I'm saying that xi are coming from p theta. Now, as teased earlier in this talk, there might be a better way to doing this, right? Can we do better than this equally weighted estimator? And this is a question that has been asked and addressed in multiple papers, and we consider a specific scenario here where p theta that we are embedding is a push forward of some tractable some tractable distributions such as uniform or Gaussian under a map g theta. Since it's a push forward, I can express this integral of interest in this form, and now it just looks like I'm integrating a function that I know quite a bit about. I will probably know something about the smoothness of g theta, probably know something about the smoothness of k, and u is a tractable distribution, so as referred earlier, we'll have closed form integrals for some well-known kernels. And this is kind of a ripe area for BQ. So we are going to construct a BQ-based estimate for this setting. And this isn't a made-up setting. It appears in simulated-based inference, where our model is expressed as a tuple of a distribution and a map that I'm calling a simulator or a generator. And to sample from the model, I sample from a distribution, apply the map, get samples from the model as an output. The generator here could be, let's say, a system of differential equations, and the getting an output requires running some type of earlier approximation scheme over a sample from a uniform. So in this setting, if I wanted to conduct inference over this model, standard likelihood-based methods would be tough to apply because evaluating the likelihood of this thing is tough because g theta can be quite complex, as is hopefully evident from my system of differential equations example. But generating sample is easy, right? The thing that I described now. Easy in the sense of I know how to code it, but it might still take a long time because this guy might be really expensive. So a solution that exists in the space, it's rather simplistic, but this is more for the purpose of visualizing the usefulness of BQ. A solution that exists is, instead of maximizing likelihood, we can minimize MMD between samples and use this notion to conduct either parameter estimation or approximate Bayesian inference over this model. Okay, so back to the problem at hand. I'm needing to approximate this kernel mean embedding I'm going to go back to the previous slide for a second, to evaluate this MMD and conduct inference over the model. Since B theta is a push forward of U over G theta, this holds, and I'm going to approximate this. I'm going to now treat this object as just a function and approximate this integral with the use of Bayesian quadrature. And the kernel C that I'm placing, that I'm using in the GP prior that is placed on this guy. So this is a little bit convoluted to think about because now there are two kernels. Remember, I'm treating this as some arbitrary complicated functions, and it can be complicated because this guy is complicated. And I am going to model it with a Gaussian process with a prior C and construct a BQ estimate with BQ weights for some kernel C on the space. This is just for clarity that C is acting on the space U, which is the input space for the generator. And we're claiming that these weights are optimal in a sense. They're optimal because the error, for more details, I'll refer you to the paper, but they're optimal because the error in MMD approximation can be tightly bounded by a term that is minimized when the weights are equal to these BQ weights. And with these optimal weights based on an additional introduced kernel, we can show that this new estimate for the kernel mean embedding leads to a new estimate for the MFD. And for regular enough, this is ordered funny, input space U, output space X, and distribution U, the error between the true MFD and the approximation based on these optimal weights, W star optimal weights, is bounded as this term, which is where nu C is the smoothness of the newly introduced kernel. This is something I can choose. S is the dimensionality of the space U, the input space of the generator. Yeah, notice that this is better than the rate for the V statistic if I were to weigh all of the samples equally, which is the default. Now, this gets better if, so C is a kernel that I can choose. So this, my impulse might be to just pick C that is infinitely smooth, because then this is so great. But this result only holds when C is less smooth than both the kernel K and the generated G theta. So this is a bit of a trade-off, in that I really don't want to pick C that exceeds the smoothness of either. And I might not, I might know the smoothness of K exactly, but the generated G theta is, again, back to the example of a system of differential equations. I can guess what the Sobolev smoothness is or test for it, but I won't know exactly. So this is a bit of a, yeah, the closer I can get to the smoothness, the better, the tighter this bound becomes as well. And these are some experimental results for the method, where we are approximating MMD with the optimal weights and using MMD minimization to conduct ABC and get this ABC posterior. And here in blue, we have the posterior based on the V-statistic approximation of MMD, and in orange, the optimally weighted one. And the dotted line is the true value of the parameter. This is inference on a wind farm model, where the parameter theta, I think, is the direction of the wind. And from the measurements from the simulator, we want to deduce what the direction of the wind was. And this is a somewhat toy example, in that we know what the true value was. Well, it's not toy, we ran the simulator, so we know what the input value was. And yeah, the message here is the optimally weighted estimator is more peaked around the true value of theta, true value of the wind angle. Yeah. Yes. That's it on this project, where we use BQ for better MMD estimates. And I talked a lot about, yes, here I talked a lot about simulation-based inference, because this was the area of interest. But really, if you're evaluating MMD between some distribution and another distribution, and at least one of them is a push forward of something tractable under a smooth map, I suggest that this is tried. This will probably work well. It's kind of a very BQ friendly setup. Are there any questions? Yes.
So look at P theta as a parameterized.
Say again?
If P of theta is a parameterized family of measures,
parameterized family. Let me go back to a. Well, maybe this is good. Yeah. So I never said what theta was. I was just kind of imagining a scenario where theta is some parameter of the generator, and I want to conduct statistical inference on the value of that parameter. So this is what theta is. And the choice of theta implies what p theta might look like. I think I misunderstood your question
you have
though.
a family of measures parameterized by theta.
Yes, yeah. P theta is a family measure parameter.
Whereas Q is arbitrary, it doesn't depend on the parameter space.
Q doesn't depend on the parameter space. So in this setup, Q is, okay, well, this holds for any Q, right? But the motivation is I have data from the real world, and the real world is Q. I have data from Q. I have this generator parameterized by theta that lets me produce p theta. Which theta do I choose so that the output of the simulator most closely resembles the data? Yeah.
So, is there a way to inform the choice of the kernel K?
Inform the choice of the kernel K.
Depends on theta in a way?
Kernel K. So I don't want to sound too confident about this. In our experiments here, at least with respect to the hyperparameters of K, the method wasn't super what's the word? Sensitive, thank you so much. Super sensitive to the hyperparameters of K. Well, so long as they're not crazy. K is only really used to embed p theta and Q. It's not a kernel that's used to construct a prior, so the specifics of it are less important. Well, there is some insight from this. Since I need this to hold, smoothness of C less than both smoothness of K and smoothness of G theta, this tells me just pick an RBF or like an infinitely smooth K, so that at least K cannot be at fault for you violating this. Now that I say this, the gap here between the bound and the actual error, it will be greater if the gap between K and C is. If you're interested in the topic, I think we should talk separately because this is the whole, whole thing. So to guarantee this fast convergence, smoother K is probably better, but the bigger the gap between K and C, the bigger the gap between this between this bound and the actual error, which might be optimal. Are there more questions about this? Yes.
Actually, quick one. So, what role did the kernel C here play? I think I've seen only K. So, what was C here?
Oh, let me go back. Yes. I need to approximate this, right? And because of p theta being a push forward, it's equal to this guy. Now I'm treating k of x comma g theta blah, 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 blah. As a function of u, I'm treating this as just some unknown function, this guy, as some unknown function of u, and I am modeling it with a Gaussian process with kernel C.
I guess his question then was about actually that kernel C depends on theta.
Oh, was it about kernel C?
I suppose.
Both. C depending on theta. Oh.
Oh, it's a
Natural world. Oh, it's massive. Wow. Yes. I still think that K depending on K is not such a huge deal, but C probably is. I think a better version of this method would also do a gradient optimization to, let's say, if the task is to find an optimal theta. And during these gradient optimization steps, I think, yes, the kernel C should be changed. How it should be selected based on what we know about G theta don't know. Open question. There is probably a relation, because C is being used to model this guy, right? So yeah, changes in theta should affect C. We are kind of implicitly, well, we're not assuming this. In the experiments, we're assuming this, that the smoothness of G theta does not depend on theta, which of course may not be the case. Okay. The second family of work that I wanted to talk about on extending Bayesian quadrature to problems where the integrals are either conditional expectations or nested expectations. Okay, so the problem that I'm considering is one of estimating the function I of theta that is a conditional expectation of some function of two variables, and the measure here is parameterized by theta. And let's say the input data, this is amazing, the input data to the problem, it's attracted to the light. The input data to the problem are evaluations of the function f at various points x, comma, theta, and let's say I have t thetas, theta 1, theta 2, theta t, and for each theta I have x, and for each theta I have n values of x against which f is evaluated. If I only needed the value of I of theta at the theta 1 to theta t points, arguably taking, let's say I'm only interested in the value of I of theta at theta 1, I can just take these evaluations and be happy with it. But that means that every time I want to evaluate I at some new theta, I'm conducting all of this work, re-evaluating f, and again, we're in a scenario where f can be quite expensive. So we're going to extend the Bayesian quadrature framework to this and say, okay, now if I need I of theta at some theta t plus 1, if it's sufficiently close to these thetas, I will not need to reevaluate f. I will just use this data for the estimation. And this problem appears in lots of applications, from general statistics, like computing moment generating functions, characteristic functions, cumulative distribution functions. It's fairly common in mathematical finance. Example problems are conditional value at risk or option pricing. And for sensitivity analysis of any model or experiment where I am interested if how the expected outcome depends on the, let's say, prior parameters chosen for the experiment. So here is the proposed method. Here's the proposed method. It is a two-stage method where in stage 1 we are using Bayesian quadrature to get an estimate of I of theta on each available theta 1 to theta t. So note that here the uncertainty over the function might vary depending on theta 1, depending on the value of the theta. And we're going to use this fact to better model I of theta by estimating it via heteroscedastic GPU regression, where the noise will be scaled with the variance of the BQ method from the previous stage. This is where having some uncertainty quantification in stage 1 really helps us, because it tells us how much should I trust the value I of theta I for each theta I. We get convergence results that come from the TQ theory, where the L2 norm of the error between the true I of theta and the proposed conditional Bayesian quadrature estimate is bounded by this guy, which is smoothness of. If you're missing the -1/2 term, that's because I slightly changed what the term smoothness meant here. I apologize for that, but it is the same thing as in the previous slide, just slightly changed terminology. Smoothness of the function f in the x parameter divided by the dimensionality of the x space, plus a bound in the number of theta points to the power -1/4. -1/4 is not great. We should have been able to get a similar non-parametric rate in T as we did in N. And this is only really happening because the proof went via connections to weighted kernel ridge regression. We just need results for heteroscedastic GP regression that match this. But yes, we didn't do this. But if we move away from heteroscedastic regression into homoscedastic regression, so forget about the quantification of uncertainty from stage 1 and instead treat all points as the same, but also use some asymptotics of regularizers that exist in KRR, then we can get a stage 2 bound of the expected. We can get the expected rate, this not parametric rate here. Experimentally, and somewhat unfortunately, the homoscedastic regression here didn't underperform the heteroscedastic one. But yeah, I think both are still worth trying, and this result should just be improved. An example of conditional Bayesian quadrature applied against some competing methods for conditional integration. So this is a sensitivity analysis problem sensitivity analysis on two problems. This is on the on the SEER model, where we want to know how much the choice of the prior on the infection rate affects the expected peak number of infected. And this is root mean squared error between the true value calculated with many Monte Carlo runs to simulate the true value, and the estimate provided by the method. Just for the sake of this graph, we set the number of theta points to be 15, but it doesn't depend on the number of points t. The relative performance of the method stays the same on arbitrary values of t. And as the number of evaluations in x grows, the CBQ method, where we use I mentioned earlier briefly the need to use a Stein kernel when the measure being integrated against is funny. So here, this is what's happening here. And yeah, the method outperforms close competitors. This is a visualization of, even though Bayesian quadrature in general and conditional Bayesian quadrature in particular is expensive in that it's n cubed plus t cubed. It takes n cubed plus t cubed to evaluate because of the need to invert kernel matrices. The cost, or rather the time it takes to get one sample out of a SEER model rows, rows from right to left so quickly that if we want a more precise output from the model, which corresponds to a low step size, the time it takes to compute, to get one sample overshadows heavily the time that it takes to get a CBQ estimate. So it is, while it is expensive, it pales in comparison to the cost of obtaining one evaluation, and the faster convergence justifies the need for it. And the second problem here is a mathematical finance one, where we look at how the expected loss of a portfolio changes based on the price of a stock at the time a shock occurred. And again, so here we can use both CBQ and the Stein version, and similar dynamics. We see better performance in comparison to cheaper but less accurate competitor methods. A little PS, I thought that I wouldn't have the time for it. Well, okay. A similar principle from the conditional Bayesian quadrature method can be applied to nested integration, where, so recall that the conditional integration was just this part. I would say, what if I am also wanting to integrate against theta, and maybe there is some function applied to the inner integral. And so we refer to this guy as an inner conditional expectation and an outer. The outer is no longer conditional. So there's a regular outer expectation and an inner conditional one. And this is, again, a commonly occurring problem in scientific discovery. And the estimator follows a similar principle of a multi-stage quadrature. So here it's really kernel quadrature rather than Bayesian quadrature, because we're forgetting the variance estimate due to it being a little unwieldy, this scenario. And again, essentially conducting kernel ridge regression at every stage. And due to there is, of course, a noise in evaluations of this guy, not evaluations, approximations. So, of course, when I'm approximating the outer integral, I'm using this approximation here. So there is noise, but since it reduces at a fast, non-parametric rate due to chi-ra, the problem is effectively noiseless, and we get a nice non-parametric rate, same as in the CBQ slides, where the tilde means up to log terms. I'm a little early, but in this talk I talked about Bayesian quadrature, which is a probabilistic quadrature method that works well for problems where we don't have a lot of evaluations and we really need to extract the most out of them. In particular, it's been shown to shine where the problems are low to mid-dimensional and sufficiently smooth. And in particular, I talked about some of our work that used Bayesian quadrature. One was estimating MMD better through Bayesian quadrature when the measure is a push forward, and also expanding BQ to the conditional problems and nested problems. And these are the papers. Good, thanks.
Plenty of time for questions.
Lots of time for questions.
I have one.
Mm-hmm.
So in this work where you look at integrals and you use a noisy GP,
yes, the heteroscedastic, yes.
you have this nice plot where we can see exactly
This one, yes.
there. It reminds me a bit of a thread of works by Januszewskis and Lorich in the years 2010, where they defined a GP jointly on the x and theta space, and then they use.
Yes. Yes. Let me remember. GP on x and theta space. I recall comparing with it. Give me 1 second to. Yeah. Okay. First response is somewhat of a trivial one. This allows one to do active schemes as opposed to the joint version.
Why not?
Sorry?
Why not? Why not? Or why wouldn't it be possible?
Why not? Why not in joint version?
With the joint version?
We could do that with joint.
I think they've used that to do Bayesian optimization on the mean.
Yes. Okay, yeah, I think not true.
I was just, trying to figure out what are the
Yeah, I mean,
the pros and cons.
No, apologies. This was a work 2 years ago. We definitely considered a joint one. I'm just trying to remember what was the issue.
We can discuss
Yeah,
that
I can send you an email about this because
Sure.
it's also definitely in the paper, but I honestly don't remember.
We have more questions. Yes.
A very practical one. How do you choose the kernel in practice? So what are the considerations? How do you tell that kernel was a good choice and it was not a good choice?
In general, in Bayesian quadrature?
In any of the three methods, perhaps just...
Yeah, in any of the three methods. So the...
Maybe here, since we're just on this slide.
Yes, it didn't include the assumptions on the kernel and the space for this result, but for this to hold, we need stuff like the kernel is at least as smooth as the function. So that's the first kind of restriction. Like if the function is a I don't know, if I suspect that it's once differentiable or twice differentiable, then I shouldn't pick a kernel, it's only once differentiable. In terms, I mean, we've been using Maturans for all of these experiments. Hyperparameter-wise, the median estimator appears to work really well still. It's just been using that. Are there more aspects of kernel selection that?
Maybe getting the x's perhaps might be expensive. So can you just try out different? Do you do some kind of sensitivity analysis? How much does I of theta or I at a particular value of theta? How much does it change?
How much it changes depending on the choice of the kernel.
I guess it wouldn't be too expensive to do that, right? Because
I mean, we could have done it in the toy example. We didn't do it. So here, it's definitely sensitive to the choice of hyperparameter of the kernel. Yes. Choice of kernel smoothness, I don't want to, again, sound too confident because Hudson did the experiments here. But I think he tried just because we have that insight about smooth kernels, just picked a very smooth matron like matron 5.2 and RBF, and RBF was slightly better.
I picture myself in a practical scenario where I get, let's fix theta, I compute the integral for particular choice of length scales, say, and then I do it again, changing it a little, get a similar result.
Oh, optimizing over the length scale.
And then I pick another value of the length scale,
Oh,
I get a very different result. And then I guess I wonder, okay, which result should I trust?
Yes, okay.
How should I handle that?
Yeah. Okay. In this work, we just did the median version, but yes, absolutely. Choosing optimizer on the length scale. Let me think about it. If I had an inner loop, in this scenario, what I would do, I think you could still conduct a cross-validation based selection of the length scale. Because again, if this is a real scenario, I don't know what the true value of the integral is. So the fact that I'm getting multiple values is not telling me anything.
So would you then cross-validate over choices of x, and you want that the result is that valued, or what does cross-validation mean here?
Yeah, in cross-validation, I would also need to assume that some value is an optimal one. Yeah, that's not great.
I can jump in.
Yeah.
There are some interesting works. I don't know if Boumedian is around, but they have a kernel flow approach where they divide the data sets and do some cross-validation and try to find some values of theta that make the predictor stable over different halvings of the data sets. Because optimizing MMD will probably lead to some very undesirable effects. If you're, because you're basically changing the thermometer.
Yeah.
But something that, with the notion of stability, I think is more or less where we're going.
That makes sense. I'm concerned about the splitting of the data set because in this setting we don't have a lot of samples.
Yes.
Maybe. I mean, there will still be relative stability.
I think it's a very, very tricky question in general how to choose the kernel in MMD.
Yes.
Because you need to have a kind of superior principle to judge what's good.
There is work in testing with MMD where they use multiple length scales and combine what do they combine? I think it's just the vote of they conduct multiple tests with multiple length scales and just do like an ensemble type vote. I'm not aware of anything like that being applied outside of the testing scenario, but.
Okay, so if you go back one slide, I suppose, I guess you have data, and you're mapping the data somehow to an estimate.
Which slide?
On multiple slides, I guess, where you have like here.
This?
Yeah, in a way, that's your data on the right-hand side. You map it to an estimate.
Yeah.
And I guess we want to perhaps, look at the variability of the estimate. In that sense, indeed, like some kind of bootstrapping strategies might be possible.
Yeah, they might. Again, my only concern there is is what happens in the low data regime here, but maybe still worth trying it.
More questions? Okay, there is no more question. Thanks again.